Friday 2 to 2:50, are you free?
Wednesday 2 to 2:15.
Wednesday 2 to 2:50. Wednesday means tomorrow only, right? Tomorrow I'm already planning to take class from 4 to 6. I have something to complete tomorrow, and it will be better if I continue in continuous mode. So,
Ma'am, the problem is like next week we have CTs, ma'am. So Friday,
hmm. So after cities on that week, can we have at least class? Because I am losing all my days on cities.
Yes, ma'am. We can have after that week.
After that week, or not on that week.
No, but during CTs, how will we have classes?
No, not during cities. Do you have any empty slot on any other day?
The empty slots we have are Monday 2 to 2:50, Wednesday 2 to 2:50, and Friday 2 to 2:50.
Friday 2 to 2:50 will do for next week.
Yeah.
Then Friday 2 to 2:50 next week I'll take class. This week this will be difficult for you for cities, right?
Yes, ma'am.
yes,
Okay.
ma'am. And like when is the honor city, ma'am? It's not in timetable.
Our city is not in timetable, so we have to plan regarding your availability and my availability. So you tell me when you want to give the cities. Yes, this is not this regular course, so they are not putting this in on the timetable. So mostly people will take cities on the weekend. We have to plan. This Friday 2 to 2:50. Do you have any city?
This
This
Friday, no.
week, ma'am.
This Friday we have lab.
Next
One
next
second, I'll
Friday
check.
2 to 2:50. Oh, okay. Next Friday we are already planning for class. Then instead of class, either we can take city or maybe next week we can plan for city. Next week after this week cities. What do you
Yes,
prefer?
that will be comfortable for us also.
Okay, then I'll schedule. Uh, so this this week tomorrow I am going to take 2 hour class, and after that there is no more classes with you. Next week I am going to have one class on 10th, right?
Ma'am, instead of like two continuous hour, like if it possible, like take from 2 to 2:50 and 4 to 5, ma'am.
2 to 2:50 and
Because
then 5. Okay. Yeah, that will also do. But for me, it is better if I take continuous class. That's why.
Yeah, tomorrow continuous is fine, I think.
Yeah. Tomorrow continuous means I am going to continue one topic. So it will be better if I do things together so that it will be fresh for you also.
Yes, ma'am, it's fine.
Okay. So Friday. I'll share my screen. You can also see what I'm doing and this. Okay. Anyway. Okay, what I'm seeing in my timetable is 10th, 17th we are scheduling CT for your subject then. 17th of September. Is it okay? Or should we schedule it before before that?
No, it's fine, I think.
Okay. So I'll mark the date then. 17 is CT for you. Okay. And
Ma'am, can we have some different timings, ma'am? Because if it is 2 to 2:50, we start late also. Again, we'll have to go for lab. So can we have it in the evening time instead of
evening time you want to give city.
or
18th.
18th morning also, ma'am.
Huh?
Or
Early
Yeah,
morning.
Saturday
18th
like
morning is better, Saturday morning.
Saturday morning. Yeah, Saturday morning is fine, but not early morning. Okay.
Yeah, yeah.
we also won't wake up early.
Yeah, yeah. Okay. Okay then. English, I will tell you time. Okay. 18th
Yes, ma'am.
fine with me. I hope I don't have any webinar or anything to attend. Okay. 18th morning is fine with me. Okay. Can I edit this thing? Then this is 18th. So before that, I might give you first assignment so that you have something to practice after this. Okay, shall we start? Is there any doubt for so far classes?
No, ma'am.
Saloni only tells that she doesn't have any doubt. What about others? Pavitra, Shreyas,
Yes, ma'am, no doubt.
Yasvi,
Yes, ma'am.
Sindhu. Sindhu, you are absent last day, right?
Yes, ma'am.
Okay. Vashu, Vashu Gambhir. Your first name is Gambhir or Vashu? Vashu, right?
Vasu, yes, ma'am.
So you have seen the previous classes. I
Yes.
didn't have math classes because I was on leave. So is it okay with you or you need some help?
No, like as of now, it's manageable. I've seen the first lecture; it was fine. I'll
Okay.
continue and I'll let you know.
Okay. Okay, then we'll start. So today we are going to start the classification of randomized algorithm. So the plan for this uh, module is classification. Should I start a new board? And classification in this will have first the La Vegas algorithm and Monte Carlo algorithm. Monte Carlo has three types that you will see. Then we'll go for the approximation algorithm. Approximation randomized algorithm. And you will see how powerful these algorithms can be. Randomized algorithms where we'll have two type of approximations and we'll solve problems like TSP, SAT, then uh, what else should we do? This what it is called. Another TSP if I solve then Hamiltonian problem also we can solve. So these are the class of NPC, right? NP complete problems. And we are going to use this approximated randomized algorithm also you can say. This version of randomized algorithm to solve either the decision problem or the optimization problem version of the NP complete problems. Okay, so this is going to be our next module. This whole thing together. Okay, one thing more is, what do you mean by a decision problem? I think we have discussed this previously also. What is a decision problem?
Where algorithm will compute yes or no.
So, decision problem is we have an algorithm which, given any input, it will produce either yes or no. So, this is our approach to solve decision problem. In case of optimization problem, what is optimization problem?
A
Finding
problem
minimum or maximum.
You
optimizing
have
that.
never seen? You have seen, obviously. I can give you an example. Knapsack. Knapsack you have
Finding the
already solved.
best solution out of all.
What was best there? In knapsack, what you used to do? You used to find the amount of quantity, maximum amount of quantity or maximum amount of profit, right?
Yes,
Yes,
ma'am.
ma'am.
So, what is optimized?
So
Profit is,
Maximizing or minimizing.
given a set
yeah,
of constraints, we try to maximize or minimize the cost.
yeah. So, some profit or loss will be there. We want to minimize the loss and we want to maximize the profit. So, this is optimization problem is of two types, either maximization or minimization, and mostly they are convertible. So you can convert, given a set of constraint, you can always, mostly you can always find another set of constraint for converting it to, from maximization to minimization or from minimization to maximization. So just like profit and loss I told. So, and another thing is, given any optimization problem, you can convert it to decision problem. Also, in most cases, decision problem is equally convertible to optimization problem. Now, you may disagree with me. Think, can we always convert any optimization problem to decision problem? So, what I am telling is, optimization problem is reducible. This is called reducibility decision problem, and same is true for here also. Have you heard of this term reducibility?
Yes, ma'am.
Yes. Okay. What is reducibility?
Uh, I forgot exactly, but like we had a small definition of NP hard problems like last semester on dynamic algorithms. It was like if any problem can be reduced to okay, there was one more type of problem exactly. I mean, I forgot the name, but if it can be reducible to that, that means it's an NP hard problem. Like that's what I understood from that.
Like converting any problem 1 to problem 2 such that the complexity of the second one is lesser. So
Lesser.
that first one is reduced to the second one.
Think in abstract.
Basically, formulating an equivalent problem, I guess, ma'am.
What?
Basically, converting it into an equivalent problem, like stating it differently.
What?
Equivalent problem, like
Equivalent.
stating it differently, like using different terms or
thinking of about the same problem in a different way.
Okay, okay, but not exactly. Yeah. So in abstract way, you can think it's something like that. Both the problems are equivalent in some terms, but in general terms, they are not going to be equivalent. Just like I said, TSP might be equivalent. If you can solve TSP, you can solve Hamiltonian problem also. But those two problems are actually different problems. But complexity wise, they are same. If you can solve one problem, you can solve the other problem also. Technique wise, the solutions should be equivalent. But the problems are not at all equivalent. Okay, think in terms of this abstract way. So suppose you have problem A. How do I write? A is your problem. So you take input to A, input for A. Now you convert this, the output of A, to another algorithm's input, which is problem B, the algorithm for problem B, and then you get the solution. Now if this conversion, now this whole package, this whole thing is reducible. Okay, this is reducibility. So here what you are doing, you are converting the input, or whatever input you were supposed to get for A, to input for B. B is your algorithm, your known algorithm to which you want to reduce. A is the algorithm which is given to you but whose complexity you don't know. So A is to be reduced to B. Okay, so what you do is you convert input to A, because your given problem is A, you have to solve B. Now you take the input set of A, you take one function which will convert that input set of A to the output set, to the input set of B, and produce the output set for B. Now that output set you have to again convert to the output set for A. Okay, so in between this A to B conversion and B to A conversion, there is one function that is operating. If that function's complexity is polynomial, then you say that A is reduced to A is reducible to B in polynomial time. So it is like A to B. There is a function which converts A to B, and then the output produced, so it is said this is output, this has to be again converted to A's output. This function, same function we are going to use. Now if this function's complexity of fn is polynomial, then we will say a, I think this is the symbol n b. A is reducible to B in order of n time or n squared time. Normally in polynomial time, we may not write the value of n in this case. Okay. So reducibility is of different types. Like you are saying, you have seen this reducibility while studying the dynamic programming, the NP, PNP, NPC, NP hard conversion. At that point, reducibility was very important. So, uh, okay. So now you tell me, in using this reducibility, how can we convert this optimization problem to decision problem? Reducibility, is it okay with you? What we do in case of reducibility?
Yes, ma'am.
Okay, if you have any doubt, you can ask me.
Ma'am, small doubt, ma'am. Like
Yeah.
Fn is like the
If
function
means
to Fn is a function to get the output from B, right? Like
Fn is a function that converts A as instance of B. That is the formal definition of it. So
oh, so it
Fn converts A as instance of B.
okay. So it's
Okay.
used to convert input of A to B and output of B to A.
Yeah, exactly.
Okay, okay. So okay, fine, cool, cool. Okay.
So if we have an optimization problem, then how can we convert it to decision problem, you think? So we have now an optimization problem. So optimization problem will either do some optimization, like it can maximize, it can minimize. So maximization or minimization, max value or mean value. This it is going to produce. Now how you can convert it into decision problem, or you can reduce it into decision problem.
Ma'am, so optimization problem will give us a numerical solution mostly.
Mm-hmm.
And decision we need yes or no. So if some way we set a constraint on the output of the optimization problem.
How? Yeah, you are right. You are on the right track. How? How we
So
will do this?
something like
For example, if we have an AppSap problem and they expect us to, like, they give us an input and they expect us to check if the output is greater than 17, like based on the input. So then we can just give a final condition that if it's greater than 17, then print yes. So in that way, it's a decision problem, right?
Exactly. So we have to suppose we know the maximum value. So in this case, optimization problem is going to give us a value, whether it is maximum or not. That is the decision problem. In case of maximization, so maximum value you have to give, that you have to provide, you have to check whether that value is matching with the value obtained. If it is matching, your decision problem will give you yes answer. If it is not matching, your decision problem will give no answer. So this conversion is polynomial conversion, because you are just simply using an equality function that will give you the answer. So in this way you can convert the optimization problem to decision problem. Now the reverse one, how can you do? Now you have a decision problem. You want to convert it into optimization problem. How do you do that?
Basically, like you give a particular period input, you already have the maximum or minimum value. If it is greater than that, no, it's not. It's wrong.
And I guess a decision problem works on the idea that, for example, if we have a graph and we want to find a path between two nodes, we can just check that the path exists. But to get the optimization, like to get the best path, we have to use an optimization problem. So then we have to add certain constraints. So that we can convert into a decision to optimization problem.
So you cannot convert optimization to decision to optimization problem. That's what you're telling.
No, I'm saying we can like I don't know how exactly, but like decision, it's about just checking if a certain condition based on the problem if that exists. Whereas we can convert it to, yeah, I'm not sure, man. Yeah, I'm not sure.
I think we can't convert.
You can't convert it.
I feel like we can't.
Okay.
Like that can depend on the problem. And like if we want, suppose if we want to find a path between two nodes in a graph, so we can just simply like use simple DFS algorithm to check that. But then we want to find the most efficient path that takes the minimum cost, then we have to use the extra algorithm. So that's an optimization problem.
Hmm.
It uses a similar problem, but it's just optimized. Like
Okay.
it gives us the best path.
See, for every problem, any kind of problem, be it optimization problem or decision problem, there are two versions of it. One is optimization, one will be decision. Okay. So suppose optimization, here you are telling max value, mean value. It can be only one value is there. There is no other value. In that case, it should be simply a numerical problem. So think in this way. Even for your searching problem is a decision problem, right? By definition, searching problem is a decision problem. Now, how you can convert it into a numerical problem or optimization problem?
Right. So you basically like going by searching, like you check whether whatever input is there is the minimum, global minimum, like multiple local minimums and global
Like
minimum will
this,
be there. You check it.
No, no, no. Searching means
add
nothing even.
weights, add weights and find the shortest path.
Mhm. No, simpler than that. More simpler than that.
Number
You
of
give
edges
two
taken,
tests.
minimize the number of edges.
No, no. Why you are complicating things? In case of searching algorithm, what you do? You check whether your given key exists or not, right? If it doesn't exist, you will give a no answer. If it exists, you will give yes answer. So along with that, what you can could have done? You could have given the location of its existence. It can have multiple existence. You can give all the possible existence of it. This will be your numerical algorithm, the numerical version of it of the same problem. Similarly, think of TSP, traveling salesman problem. Traveling salesman problem, the problem means you have to find the optimum path uh, which travels all the cities and comes back to the starting point. That is the uh, that is the optimization problem. Now, how you can convert it to the decision problem? You have to tell that whether a given one, once you have given a solution, once you have derived a solution or given a solution, you have to check whether that is your optimal path or not. That is the valid solution or not. Okay, that's why there is this NPC and NP hard. These two type of problems that have come into existence. So similarly, NP hard problem is NPC problem is what your validity checking of whether that solution, one solution you have derived using your optimization problem for say TSP. Now that solution is actually a solution or not, that you have to check. That is your decision problem. So if it is a solution, you will say yes. If it is not a solution, you will say no. Similarly, for knapsack problem, say maximum value you have obtained by some method, any algorithm. It doesn't matter which algorithm. You have obtained some algorithm, some value, then you have to check whether that is the desired solution or not. So we are converting into decision problem. Now your optimization problem is what? You have to obtain the actual value. If it is yes or no, doesn't matter. You have to obtain the value. That is your decision. That is your optimization problem. So similarly, for any problem, whenever you are deriving the solution, mostly it will have a numerical value solution along with the decision problem solution. Okay, for all kind of problems. And as we have started here, so maybe I should explain these things to you too. I don't know whether you are familiar with it or not. So for optimization problems, to solve optimization problems, you can understand that optimization problems are more hard. So optimization problem solution, we go for, so this mostly form the class of NP hard problems. And decision problem, once we convert it into decision problem, in case of decision problem it is pretty easy because you are given a solution, you just have to verify it whether that is a solution or not. Uh, Still, it can be NP complete. Not all, obviously. Some. Okay, I was supposed to start something else. Do you have clear idea about this NP hard, NP complete, or everything? This NP group of class of NP. We'll be using this again in this in the next part, like when we will be talking about approximation algorithm, because we are going to solve some of the NP hard or NP complete problems using this randomized approach. Do you have clear idea, or I should explain some more?
Ma'am, I think you can explain some more because you only know the definitions.
Okay, what is the definition you know? What what stands for NP? Can you tell?
Non-deterministic polynomial.
Yeah, good. Non-deterministic polynomial. Now, from where this non-deterministic comes?
Turing machine, basically, what it basically tells is you given a set of problem and a Turing machine to give it multiple states, like a Turing machine getting multiple moves as such, and we don't know at what particular state what move to take. So that is how the non-determinism comes in therefore.
Okay, so you are going to use a NDTM,
Yes.
non-deterministic Turing machine. Okay, then what is meant by NP problem?
I
Yeah,
didn't get you. What is meant by
NP problems.
NP problem? So whatever this one these problems can be solved in polynomial time and in the non-deterministic Turing machine.
Yeah, exactly. So NP means it will, it can be solved in polynomial time by a NDTM. Okay. Now, if it is solved by an NDTM in polynomial time, why it is difficult? Why are we bothered about NP? Why we always want to convert it into P?
So they can be verified.
Mm-hmm. No. Verified is
To
okay.
make it faster,
That is
more
not the
efficient.
exact answer.
Am I
Faster.
audible now?
Okay.
Oh, yeah.
Why? You are saying that NDTM is going to give us solution in polynomial time. So we are getting polynomial time solution, right? Then why we are not happy with it?
I think NP is more like it can be verified. The solution can be verified in polynomial time. That's what NP means.
Okay, that is the Coleman's definition. Yeah, that is the definition from Coleman's book.
Yeah, so
Ma'am,
that clearly means we can't solve it in polynomial time, right?
Okay.
as the name suggests, NDTM, we don't know like at what point it will terminate, if at all it terminates.
So we
No.
want to solve it by deterministic methods, right?
Yeah, exactly. We want to solve it by deterministic method, and we are not happy with non-deterministic solution. Non-deterministic solution means it is okay, it is going to terminate. It's not like it is not never going to terminate. We don't know when to terminate. It's not like that. It is obviously going to terminate at some point of time. That we have to prove. To prove that one problem is in NP, you have to first show that it is going to be solved by an NDTM in polynomial time. Okay, but the point is it is non-deterministic, but we want deterministic solution. So P means, when we are talking about P, we are talking about deterministic Turing machine, DTM. I don't know whether you have studied Turing machine in details or not. Turing machine is very interesting. So and this is the base of all, like all complexity theory, Turing machine. So
We did a little bit on.
yeah, that is the that is the problem with this.
But because the thing was, it was at the end of the course, so we
Yeah,
kind of rushed.
yeah. Every time it happens like this. So if I am given this course, I will start from this TV mission. This is always it is left out, and it is important for every other classes. If you leave it in automata theory, you will never going to get it in algorithm. Then any advanced version of algorithm will also be skipped. Similarly, it will be left out in compiler design, but it is basic. You need to know this. Anyway, you can self-study also, and if you need help, I am there. Okay, so P means deterministic Turing machine. This will solve the problem in polynomial time. Polynomial time, we write it in order of n to the power n to the power k. Order you know already, BO notation n to the power k means it is polynomial time, right? So deterministic Turing machine, and here what we are getting is non-deterministic Turing machine. Another theorem that you should know is, for any non-deterministic Turing machine, you can always get a deterministic Turing machine. So power of deterministic Turing machine and non-deterministic Turing machine are equivalent, just like you have studied in NFA and DFA. For DFA, you can always get an non-deterministic finite state automata, right? You remember that? NFA DFA conversion was there.
Yes.
Why so shy? You have forgotten that part also.
No, we had. Yeah, we learned that.
Okay, so in that case, there is some problem. You remember that when you convert from NFA to DFA, there was in some cases, like in one conversion, some state change was there. In which case, it was more number of states were required. Can you remember?
NFA, right?
DFL a more number of
No,
states.
states
DF
DFA will have more.
more
Yeah.
number.
Yeah. So if you want to convert an NFA non-deterministic automata to a deterministic automata, you have to increase the number of states. So number of states increase means complexity wise it is increasing. You have to deal with more number of states means more complex the situation is. Similarly, so but the power is same. Power is same is in the term both of them can solve the same problem. Both of them cannot solve, one cannot solve a problem which cannot be solved by the other. In that term, they say that the power is equivalent. Okay, that is the term of equivalence in case of this automata theory. Now, if you take this NDTM and DTM, they will say that DTM and NDTM both are also having same power. Same power means both can solve the same problem. So if you have a NDTM which is solving a problem in polynomial time, you can always get and DTM which will also solve that problem. But at which cost? Cost might be increased, just like in NFA and DFA you have seen that for NFA to DFA conversion, the cost in terms of number of states, that is increased. So here I am writing down the theorem. This theorem tells that for any NDTM, there is always an equivalent DTM which solves the same problem in not more than c to the power right. What do you understand? If we have an NDTM that is solving a problem in time t, we can always get a DTM which also solves the same problem, but here the time will be c to the power t, where c is at least greater than 1. Greater than or equals to 1. Equals to 1 means it is going to be 1 to the power t means 1. No constant time. No. Yeah, it will be greater than 1. So it is going to be greater than. So if you have say t time, it is going to get at least 2 to the power t time. 2 to the power t means exponential. That's why you are not happy with the NDTM solution. Even though it is going to give a solution in polynomial time, but if we solve it, if we convert it into deterministic solution, we are going to get exponential solution time. That is the problem with NP. Okay, is it clear now why we are not happy with this non-deterministic Turing machine solving in polynomial time? Any doubt?
No doubts, ma'am.
Yeah, tell me.
No doubts, ma'am. No
No
doubts.
doubts. Okay, good. Okay, so this is why we call this class as NP, non-deterministic polynomial time solution.
Ma'am, I have a doubt actually.
Huh?
I have a doubt. So, in this theorem, the time t taken by the NTTM is shouldn't like be the optimal time because since at any state, since at some state it would have multiple the NTTM would have multiple choices to make, and we
Yeah,
would
yeah, it
be
is like
relying that.
minimum time.
Okay,
Solution is always in minimum time.
okay,
If you know a solution is say uh, is taking 10 time instance and one solution is taking 15 time instance, obviously we will go for 10 time instance, right? So whenever you are
yes,
talking
ma'am.
about solution, it is always optimal
Okay,
solution.
yeah, yes, ma'am, got it.
So what do you know about this NPC, NP complete? Okay, another question for you. What is the relation between the class of P and class of NP? Can we say P is a subset of NP?
be a subset of NP.
Yes, ma'am, we can say.
Yes, ma'am.
Proper subset? This or this?
Proper subset.
Proper subset, not all P contain.
We don't know it now.
Who is that? Shreyas, right?
Yes.
We don't know it. That is a $1,000,000 question. Whether it is proper subset or not. That is really a $1,000,000 question, okay? If anyone is going to prove it, you are going to be millionaire. Okay. By definition, P is going to be subset of NP, but we don't know whether NP is whether there exists something in P which is not included in NP or not. So whether it is proper subset or not, that we don't know. That is because of this complicating class that is called NP complete. So once we know for sure whether this NP complete class is tractable or intractable, I am going to use another word, tractable or intractable, then it will be pretty clear whether this is P is subset, proper subset of NP, or P is only subset of NP, or P equals to NP. So that is still a vague condition, although mostly the computer scientists believe that P is proper subset of NP, that is P not equals to NP, so we mostly believe, although I am not a computer scientist, but mostly people think that, most people believe P is proper subset of NP and P obviously is not equals to NP. That is the belief, but it is not true. Okay, what is NP complete? Anyone with the definition? Quick. Definition at least. Are you there?
Yes, ma'am. Not definition as such, but like solution can be found and verified, and all possible solutions can be found.
Solution can be found or verified. Found and verified.
Yeah, I think so.
Verified.
Only verified or found and verified?
Found and verified.
In P time.
Mm, yeah.
Okay.
Only verified, ma'am.
Only verified, right?
Only verified or found and verified. There are two things, NP complete and NP hard. Okay, NP complete, you can write in this way. You should take all language L such that L belongs to NP. That is the first condition. So the language we are talking about, or the solution we are talking about, are part of the NP set, and for all L dashed in NP, L dashed is reducible to L in polynomial time. P. Oh, I have written N before, no? I should change this to P. This is supposed to be P. This is the definition. What does this definition means? So for one problem to be proved as NP complete, what you have to do is, first you have to um, find an NDTM that solves it in order of n to the power k time. This will make the problem as NP. Then reduce this problem. The better way to do is the reverse thing actually. See, here what we are doing is we are proving that all problems in NP can be shown as instances of this problem. Now there is some problems which are already proved to be NPC, just like the first problem was SAT, then TSP is there, click problem is there, uh, Hamiltonian problem is there, several other problems are there. So whenever a new problem comes and the researcher seems that this problem is going to be almost, it is not solvable in polynomial time, their hunch is like that, then they try to prove it to be NPC. So once you have proved it to be NPC, you are almost done. Then no one is going to question your complexity. But to do that, what you have to do is you have to find an non-deterministic polynomial solution, that is NDTM, which solves it in polynomial time. That is important. This part is very important, to find the solution in polynomial time for an NDTM. Only then you can say this is NP. Then what you do is you take a known NP complete problem, just like you can take SAT problem and reduce that SAT as an instance of this new problem. So all, suppose SAT is there, all other problems, all L dash is already reduced to SAT. Now you take SAT and you reduce this SAT in polynomial time to your problem, say A. If you do this, if you are done with this, then this part, so this reducibility, this, if you study this relation is actually equivalence relation. No, it is transitive relation in this case. So L dash is reducible to SAT and SAT is reducible to A. So in that case, you can say that all other problems are also going to be reducible to A. So you can say L dash is also reducible to A in polynomial time. Reduce. So your target will be reduce a known NPC problem in polynomial time to your problem. So if you do this, you are done. Now in terms of Coleman's logic, obviously he doesn't go for this non-deterministic Turing machine version. He prefers the solution and verification. So you have a certificate. So for NPC, you can find the certificate and you can verify the certificate. Finding the solution is equivalent to telling that you can find the certificate. So this is finding the certificate. And this reducing any known problem to pure problem in polynomial time, this will be equivalent to verification of certificate. So that's why for NP complete problem you have both, you can both find the solution and verify it in polynomial time. So this solution is called certificate. So it is another term. You can find this in that Coleman's book. So this is about NPC. About what is happening now for NP hard. NP hard. Once you know NPC, NP hard is almost similar. In case of NP hard, you don't have to prove that a non-deterministic polynomial time solution exists. You just have to prove all solutions in all problems in NP or whatever language exists in NP, those are reducible to this new language you are designing. So this is L such that for all L dash belongs to NP, L dash is reducible in polynomial time to L. So for NP hard, no need to find polynomial time solution by a non-deterministic Turing machine. So in this case, if your certificate is given to you, you can verify it in polynomial time. Because here, see, here this is polynomial, this reducibility is polynomial. So if certificate is given to you, you can verify a given certificate in polynomial time. So if we talk about TSP where you have to find the solution, that is NP hard, that is optimization problem. That solution you cannot find in polynomial time. But once a solution is given, you can verify the solution. That's why the decision problem version becomes NPC. So for example, TSP has optimization version, optimization version. This is NP hard, decision problem. This is NP input. Okay, I was supposed to talk about La Vegas and Monte Carlo, but I instead talked about something else totally. Is this things clear to you? I don't want any of you to have any doubt in regarding these things. Is it clear?
Yes, ma'am, it's clear.
Yes, ma'am.
Yes.
Okay. So if you have any doubt still on this, you can ask me next class also. Because this is going to be useful for your rest of your life. If you are going to be in research, if you are going to be in some industry, doesn't matter. This is going to be useful. Okay, so maybe I should stop. Presenting.